So now we go from pre-stellar cores to the solar atmosphere. We will have Ryan Hofmann, who is a PhD student at University of Colorado and the National Solar Observatory, and he will be talking about spectroscopic inversions.
Okay, thank you for the introduction. Hello, everyone. I am Ryan Hofmann. I am a PhD student here at the University of Colorado Boulder, and I'm going to be telling you about some work that I've been doing with Kevin Reardon and Ivan Milic here at CU and National Solar Observatory. So the main thing that I study is the chromosphere. So what is that? I'm assuming some of you are at least somewhat familiar, but essentially the chromosphere is the middle layer of the sun's atmosphere. It's where the temperature starts rising after falling off in the photosphere with height. And then the temperature quickly shoots up even more, which we call the coronal heating problem. So there's a lot of information here on this slide, but the main thing that I want you to take away here is that we have sort of these 1D models of the average sort of temperature structure of the sun's atmosphere, but those really sweep under the rug or just hide a lot of the intricate complexities of the sun's atmosphere that are very relevant to various questions that we want to answer. Things like, where is the energy coming from to heat the gas here? Where is that energy going? How is it dissipated? That sort of thing. There's several ways that we can study the temperature of the chromosphere. Historically, it's mostly been through strong spectral lines like the calcium H and K, the magnesium B lines, infrared lines. But now with ALMA, we can also study it in the millimeter continuum. So speaking of lines, our main way of studying the sun's atmosphere thus far has been through what we call spectral inversions. And an inversion is, as the name might suggest, an inverse problem, quote unquote. So essentially, you're taking the value of an observation and trying to find the combination of parameters along your line of sight that produce that observation. So the way an inversion works, you can sort of see the process here in this animated GIF, is that you try to find the atmospheric parameters along your line of sight, given a spatially and temporally resolved observed spectrum, which you can see here in red. You try to seek a generating atmosphere starting from a guess model. You can see that here in the orange lines. And then you use radiative transfer calculations to produce a synthetic spectrum, which you can see in the dashed blue lines. And you iteratively perturb your guess model and use least squares minimization to try to find a best fit model. This is great in and of itself, but there's some inherent problems. For one thing, for chromospheric lines in particular, it requires a very complicated radiative transfer calculation that treats the radiation and the gas in non-LTE. So whereas for photospheric lines, you can make the assumption of local thermodynamic equilibrium, where the radiation is coupled to the local gas temperature. Here, it's not that simple. You have to account for radiation from distant sources influencing the populations of various levels, and that makes it a lot more complicated. It's an ill-posed minimization problem, which means that there are multiple possible solutions that could give you the same observed spectrum. There's a lot of free parameters that you're trying to fit for, and it's very computationally expensive. So for a typical inversion of a chromospheric line, you might spend anywhere from a few minutes to upwards of an hour trying to invert just one single spectrum. And with modern instruments, you get millions of spectra in less than a minute. So this is not exactly super viable for large scale stuff. Now, where ALMA comes in is that we can use ALMA observations just to directly measure the temperature of the chromosphere without having to worry about doing inversions, theoretically. So what we're looking at here is the millimeter continuum. So no lines involved, just the continuum. And it's formed from what's called thermal Bremsstrahlung. So just, I'm assuming that you're somewhat familiar with that, just the radiation from charged particles, say electrons, moving through the plasma and slowing down as they encounter various ions. So this is a continuum emission. It's formed in LTE, so the radiation that we see here is very strongly coupled to the Planck function. And since we're looking in the Rayleigh-Jeans regime, so the long tail of the Planck function, this essentially acts as a linear thermometer. You can see here that, for instance, in H alpha, we see these active regions at various points across the solar disk. And if you look at the ALMA observations, they very strongly correlate with these active regions. The chromosphere we see is apparently hotter in those active regions. And this is just a direct observation, which is great. So one thing that we can theoretically do with this is use ALMA observations to test our inversion results. So as it happens, because of the way that the opacity of the electron gas that you're looking into with ALMA varies based on the wavelength, different ALMA bands sample various heights in the solar atmosphere. And you can see that here in this figure. This is basically taking a sort of a MHD model of the sun's atmosphere and sort of just making a histogram of where the radiation in these various bands is coming from as a function of height in kilometers above the solar surface. And you can see that these distributions peak at very distinct heights, although there is a lot of spread even for these most separated bands. The ones that we're mostly concerned with here are around 1 millimeter and 3 millimeters. So it's great that we can actually use ALMA to theoretically test our inversions. In theory, we can also use ALMA as an additional constraint in our inversions to hopefully lead to a more unique solution. So in this particular case, we're looking at this target right here. This is a region of magnetic plage at the edge of this active region. For those of you who saw Momo's talk yesterday, you might recall what he said about coordinated observing campaigns. So this was a set of coordinated observations between IBIS at the Dunn Solar Telescope and ALMA. And so this is just zooming in to that region. We have the AIA images here. We have the ALMA images and the sodium and calcium line cores. So our inversions essentially, they sort of correlate well with the observed calcium line core. The temperature correlates well with that. And so hopefully, we can get some useful information out of that. Now, one thing that needs to be taken into account here is non-LTE treatment, not just of everything else, but also the ionization of hydrogen. Typically, inversions will determine the electron pressure, the electron density, just straight from the gas pressure. But that's not as valid in the more tenuous chromosphere because you have radiation also ionizing hydrogen, not in equilibrium with the thermodynamics. And so that leads you to underestimate the temperatures in the chromosphere. So in our case, we need to solve explicitly for the electron density, and this affects both the depth of the calcium line and the height of formation of the ALMA continuum. So what do we see here with these inversions and with ALMA? Well, what we see is a couple of interesting things. So if we compare the temperatures derived from the inversion of the calcium line with the temperatures observed in ALMA band 3, then we see that they have very similar large-scale spatial structures. And perhaps if the resolution on ALMA was better, then we would see a tighter correlation. We also see significantly higher temperatures, about 2,500 Kelvin higher in band 3, which is not unexpected because we expect the band 3 radiation at 3 millimeters to form higher up in the solar chromosphere.
2 minutes.
Now, when we look at band 6 as compared to the inversions, they have very similar temperature ranges, but there's a lot less spatial correlation than we would expect. And this is surprising because we think that band 6 and the calcium line should form at similar heights. So what's going on here? Well, one thing that you have to keep in mind is that we're looking at the integrated radiation along our line of sight when we're looking at the ALMA continuum. So if you take, say, a MHD model of the sun's atmosphere, like in this lower figure here, you're summing over a large range of heights, possibly as wide a range as 1,500 kilometers. And the heights that you're summing over, the width of that distribution along your line of sight varies from one spot to another, and even over fairly small timescales. So it's not exactly a trivial problem. So what does ALMA really tell us? Well, it's a nice linear thermometer, but it's not immediately obvious what it's actually measuring. MHD simulations can help us somewhat with the interpretation, but there's still not even a good consensus on what physics is necessary to reproduce all of this. So it's very non-trivial. But if we can figure this out, then we might be able to use millimeter observations as a more simple direct probe of the chromospheric temperatures in other stars, which could be very useful for characterizing potentially their UV emission as it relates to say exoplanet habitability. And with that, I will take any questions.
Thank you so much, Ryan. This is really interesting talk. I'm also really amazed how much more information you can get from the continuum maps from ALMA compared to the H-alpha line, especially the dynamical information. That was really great to see. We have time for a couple of questions. Do we have any?
So yeah, we have several. But first one, the first images that you show from the whole sun, those were taken with the ALMA total power array, right?
Sorry, could you repeat that?
At the beginning of your talk, you showed the whole disk of the sun observed from ALMA. And I guess that was from the total power array, right?
These?
Yeah.
So those are taken with a single dish antenna, right?
I believe so, yes.
I was just curious, how long does it take to map the full disk of the sun? Do you know?
I couldn't tell you for sure. I can tell you that the observations that were used for my work had a cadence of, I believe, 2 seconds for the ALMA observations. But I don't know how long it takes for ALMA to scan across the full disk for a single dish like this.
Well, the field of view is small, so it should take some time. Yes. Okay, never mind. Maybe one comment is that before I was very puzzled to see that the images from ALMA in the millimeter were very similar to the H-alpha, so I was very confused if it was worth to get ALMA to observe this. But I would like to thank you that you convinced me that you still can get a lot of information from the ALMA observation. So thank you very much for your talk and explanations. Especially, it's very. I mean, it was very interesting to see how you can really probe the different regions, the different layers. So thanks for that.
Yeah, if I can ask a question.
Yeah.
From the ALMA observations, the primary thing I noticed is that you get a lot more information about the temperature, but to understand the density profile and especially how the temperature is affecting that density, do you get that information from the ALMA observations, or do you need something else, or you have to rely only on the spectroscopic inversion modeling?
Yeah, so ALMA itself doesn't really tell you anything about the density or the height of formation where the radiation is coming from. So for our study, we had to sort of just interpret that based on what the inversions produce. As I said, the inversions, they give you a height scale, but that's assuming hydrostatic equilibrium, that's assuming a bunch of other stuff. And another thing that we've found with this study is that even if you were to say include ALMA in the inversions as an extra constraint, it's not exactly straightforward, because the inversion process, even when you're treating hydrogen ionization in non-LTE, because of the strong coupling of the continuum emission to the exact electron opacity, and depending on whether there have been various time-dependent effects, say that a shock went through recently, and so there's still a lot of extra free electrons boosting the opacity, that can really throw things off, and especially with the band 6, which forms at sort of a similar height range, the code ends up fighting with itself and making a very difficult to interpret mess. So again, just because the band 6 especially seems to form over such a wide range of heights, it's not at all straightforward to interpret these observations. So yeah, it's complicated, and it can be frustrating too.
Yeah, I can imagine. Yeah, modeling the solar atmosphere is never easy.